Hey class, here we are with lesson 2 of unit 5. We're now getting into the dynamics of uniform circular motion. So if you missed our first lesson on kinematics, I recommend you go back and look at that, as it's all built on top of each other. So if we think about kinematics as being the speed and the acceleration, dynamics now is all about the forces, just like our third unit, dynamics. Force is equal to mass times acceleration, which we can see right here is the same formula we're using with our centripetal force. So since an object in uniform circular motion is still accelerating, even though it's a different type of acceleration, our centripetal acceleration, there still is an acceleration, so there must be a net force. And it needs to be acting towards the center of the circle, because that's the direction that the acceleration is. The direction of the force and the acceleration need to be matching, which for all three of these they are. So we're going to name this, or label it, our centripetal force. So don't get confused with centrifugal force. That's not something that we talk about. It doesn't even exist in high school physics. Centripetal, right, is the force towards the center. Center, centripetal, there we go. Take this note into mind. This is important. It's not a new type of force. It's a new label for forces that we already have when they are acting as this force towards the center in the same direction of our centripetal acceleration. So it's not a new distinct force, it's only a label. A label. Don't know what a label is. So it is going to tell you which force is responsible for this centripetal acceleration, or for turning the object. So, right, we remember that centripetal acceleration is all about changing the direction of our speed. So this is the force that's responsible for changing that direction, or turning our object. But as you see here, centripetal force can be many different types of forces, as long as that force is creating our centripetal acceleration. So when we're driving in a horizontal circle, right, pulling out some donuts in the parking lot, then we have friction as our centripetal force. That's the one that's turning the object. That's the one that's changing our direction of our speed. Our centripetal acceleration is created by the friction on our tires. And similarly, when a satellite's in orbit, it continues to turn around the planet that it's orbiting because of gravity. So those are just two examples, right? We could also have a yo-yo with a string. Now the tension force in the string is our centripetal force, and the list goes on and on. So that's all of our notes for today. We didn't even really get a new formula. We're just adding a C to our existing formula. You'll see that here our net force is only our centripetal force. So that means that there's no air resistance, there's no friction or anything like that. The only force acting on our object that's creating the entire net force is this centripetal force, when we're looking at circular motion anyways. All right, let's take a look at our examples. So our first example, we have one of these rides. Maybe I'll post a link to this in case you haven't seen this ride before. It's pretty awesome. But essentially, right, you have a person who's in this centrifuge ride, right? It's like a big cylinder that spins around super fast. And that person is kind of being held against the wall, right, by this idea of centripetal force and inertia and Newton's third law. So there's a whole bunch of things coming into here, but we're just going to focus on our centripetal force here. So the person has a mass of 76 kilograms. They are being whirled in this horizontal circle, right? So gravity will be down, right? And they're being spun in this horizontal circle. We know the diameter, not radius, of this entire centrifuge is 9 meters. And we know that the centripetal force is 5.21 kilonewtons. We want to determine the time it takes for one rotation. So we're given our centripetal force. We only have one formula that works for that. Let's write it down and see what we're missing. We have centripetal force, we have mass, we are missing centripetal acceleration. So that's what I'm going to focus on. Centripetal acceleration solved is the centripetal force divided by the mass. Remember, we're working with kilonewtons and our standard is a newton, so we'll have to multiply it by 1,000 to get 5,210 newtons, divided by our mass of 76 kilograms. We have a centripetal acceleration of 68.55 meters per second squared. All right, we know centripetal acceleration. We want to get period. All right, there's this other piece of information given to us, diameter. So I'll just start by writing our two general forms for centripetal acceleration, speed squared over radius, or 4 pi squared r over period squared. Do we know anything about speed in this question? Are they talking about speed at all? Can we solve for it? Truth is no. We don't want to be working with speed. We want to find the time it takes for one revolution, which is our period. That's what we're looking for. Do we know radius? Sort of. We know diameter, and we know that diameter is equal to 2 times the radius. Sorry, the 2 looks like a D. So our radius is equal to diameter over 2, which in this case is 4.5 meters. We have everything we need to solve for period. So I'm going to rearrange this, solving for period. Period is equal to 4 pi squared times radius divided by centripetal acceleration. Throw in everything I know. 4 pi squared is a constant. My radius is 4.5 meters. And this would be t squared still. Don't forget the little square. And I'm dividing it by the centripetal acceleration, which I calculated to be 68.55. I'll use the whole stored value in my calculator, so I avoid any rounding errors. Now, we need to take the square root to get rid of the squared. So period is equal to the square root of 4 pi squared times 4.5 divided by 68.55, giving us a period of 1.61 seconds. So it takes this centrifuge 1.6 seconds to complete a loop. Ooh, sorry if you're getting dizzy. All right, next example, we're working with a car rounding a corner. So again, this is an example of a horizontal circle. A car is turning, right? Maybe drifting, who knows. But let's look at our free body diagram of this car in the horizontal direction. So we know there's a force of gravity and there's a normal force. Let's say the car is coming at me out of the page, and this is kind of the circle it's going on, up, back, down, which means it will be accelerating towards the center of that circle with this centripetal acceleration. And again, from the note, the force that is producing this centripetal acceleration whenever we're dealing with a car is going to be force of friction. That's because it's our tires that are gripping to the ground that are allowing us to turn, right? So whatever force causes us to turn is going to be our centripetal force to turn. That will be our Fc. So here, force of friction is our centripetal force. In our diagram, we want to determine its maximum speed, right? So speed max is what we're looking for. We know that the radius of the corner that we're turning is 100 meters. And we know we have a static friction coefficient. We're working with static rather than kinetic because unless our tires are skidding, right, and we're actually in a drift or a skid situation, we still have this static condition with our tires on the ground. They're not actually slipping past each other, right? And until those two surfaces are actually sliding over one another, right? Until they're sliding, we're still working with static because they're still gripping right against each other. They haven't yet broke that resistance. They haven't split apart. They haven't started drifting. So we're working with static coefficient of friction, and it's given as 0.5. No units. Okay, in order to do any of this, right, we're going to need to solve for the force of friction. So in our force of friction formula, we need to have this guy times our normal force. So that's going to be our first step to solve. So when we look at our free body diagram, and we especially look in the vertical direction, that's where we're going to start. We know that there's uniform motion, no acceleration. So we're going to use principle of physics 0, Newton's first law. The net force is 0, or our normal force is equal to the force of gravity, mass times gravity. They give us the, no, they don't give us the mass of the car. Interesting. We're going to keep it as a variable and throw it into this equation. So force of friction now, force of friction is equal to our coefficient of static friction times mass times gravity. And we're going to hope that we can cancel the mass out because it's not given to us. So that's everything in the vertical direction. Let's move to the horizontal, where we have non-zero acceleration. So we're working with accelerated motion, uniform acceleration, principle of physics 1. And we know that here we're going in a circle, right? Our car is moving around a circle, right? We're trying to figure out how fast it can go, the speed, given a radius of 100 meters. Okay, so we're looking in the horizontal direction at a horizontal circle with uniform circular motion. So I'm just going to abbreviate it as uniform circular motion, which if we look at the back of our formula sheet, we can see that uniform circular motion is actually principle of physics 2. So using principle of physics 2, assuming at our max speed we're going a constant speed, right? Vmax equals constant speed or constant magnitude of our speed. We're only changing direction. So our speed is constant, right? Because if we could go any faster, we wouldn't be at max. If we're going any slower, we're no longer at max. So Vmax must be at that constant speed. We know from today's lesson that the net force acting on the car in this horizontal uniform circular motion is equal to our centripetal force, which is our friction force, and that's going to be equal to our mass times our centripetal acceleration. So yeah, we're kind of just combining everything into one. So we know centripetal force is our mass times our centripetal acceleration, right? Here's our centripetal acceleration. We don't know our mass, but we're going to be able to substitute this into here. So if we combine this guy and this guy, we end up with our static friction times mass times gravity is equal to mass times centripetal acceleration. Look, masses cancel. That's exactly what we needed to happen. We can then break up our centripetal acceleration into its speed squared over radius, because in the end we're looking for speed. So we're not going to use 2 pi squared r over period squared. We're not looking for period, we're looking for speed. So let's just clean this up and write out solving for speed. So our masses have canceled, our acceleration is turned into this. We have our, well, I'm going to write it just with everything canceled out. Coefficient static friction times gravity is equal to speed squared over radius. Solve for speed. We're going to get a square root to get rid of our squared, and we're going to multiply both sides by radius. So radius, coefficient of friction, gravity, and throw our numbers in. Radius was 100. Our coefficient was 0.5. And gravity, of course, is 9.81. Multiply all three of those together, take their square root. We get speed is equal to 22 meters per second. We're only allowed 2 significant digits because our coefficient of static friction was only given in 2. So if you're going any faster than 22 meters per second, what's going to happen? We're going to break our static coefficient or break our static friction. We're going to start drifting, right? Our force of friction is going to decrease. We won't be able to maintain this centripetal acceleration anymore. And in short order, we're going to drift, right? We're going to veer off of our uniform circle. Our radius will no longer be 100, right? We'll continue drifting because we are going too fast. All right, there's our lessons for the week. Let me know if you have any questions at all. Hopefully this stuff is treating you well. All right, class, see you later.